Hello, and welcome to today's session on Eta Squared, Power, and Factorial ANOVA Computation. As always, before we begin, please make sure that you've got the PowerPoint lecture notes printed and in front of you so that you can take notes along the way. Today we've got lots of topics to cover, and we're going to jump right in by describing Eta Squared and Power, and we'll try to put this into some context that will make sense given the prior videos that we've had on related topics. So let's begin with a question. What does the abbreviation ANOVA stand for? Hopefully, you're very familiar with this phrase, ANOVA, and you know that it stands for the analysis of variance. So our job as psychologists is try to explain fluctuations in whatever dependent variable we might be measuring. Usually for psychologists, we're measuring something related to behaviors, thoughts, or feelings, and those dependent variables typically show lots of variation, lots of variability, and it's our job to try to explain that and account for that variability as well as we can. Sometimes we account for that variability correlationally, sometimes we're able to account for it causally, but in any case we're trying to account for that variability, we're trying to analyze the variance, and to do that we need to understand that we might have more than one independent variable affecting the outcomes of our scores or our dependent variable. So what we're going to do today is return to an idea we've seen before. This is the idea of the pie chart that represents the variability in any one of our studies. What's new today is we're going to be looking at this pie chart of variability within the context of factorial designs, which are also called complex designs. Here again we have lots of different variables, independent variables in this case, and we have their independent effects, which we might call main effects. Also we have their combined effects. And we've said on several occasions, one of our primary motivations for getting into complex designs is that we want to be able to understand how it is that multiple factors in the real world might be interacting or combining to influence the behaviors, thoughts, and feelings that psychologists are interested in investigating. So here's our pie chart, and what's a little bit different today is we have more colors than usual. Just to remind you, what we're showing here in blue is the variability associated with factor A. What we're showing here in this lime green color is the variability associated with factor B. Here in this yellow area, and I hope the colors are coming through on the video, we have the variability attributable to the combined effect of A and B. We call that the A by B interaction. And then in this red area, which in this particular pie chart is really quite large, we have the within subject variability. Okay? So here we can think again of the variability as maybe being the total sums of squares, and we're going to try to partition the sums of squares into these different components that you see here. Later on today, when we're concluding the video, we'll give you some new basic ratios for computing these sums of squares. For the moment though, we'll just try to extend what we've learned previously about partitioning the variability, as indicated by the sums of squares, into various components so that we can answer a question like this. Which effect, if any, would have a significant F value? Okay, so we'll let you stop the video and see if you can respond to this question. Okay, welcome back. Hopefully you came to the conclusion that none of these effects are going to have significant F values. Let's see if we can remember why that's the case. First of all, the F ratio, as you'll recall, is a ratio of between subject variability over within subject variability. And we have this MS between over the MS within in our ratios, and we've seen those before. Here what we can see is that we have a really large red area. This corresponds to the variability within subjects. This would make for a very large denominator. If we look at the proportion of the total pie that is occupied by, for example, the blue area, which is factor A, we see that that is quite a bit smaller than the red area. So if we were to put the variability attributable to factor A in blue over the variability attributed to the within subjects component, that's going to be our denominator, we're going to wind up with a fraction that's going to be smaller than 1, and that's going to be statistically non-significant. The same thing would be true for factor B, shown here in lime green. That is, this red area is, if you will, swamping the green area, generating a F ratio that's going to be smaller than 1. That's going to be non-significant, and even more so for our within subject, for our A by B interaction. That's going to be a very, very small fraction. Again, it's going to be positive because we're dealing with sums of squares, but it's going to be quite a bit smaller than 1. And just for a little bit of context, let's remind you of how we're coming to that conclusion. We'll take a look at the F distribution, as we've seen many times before. Here's the F distribution, And here's the equation that we've described previously. This is the F ratio, the Fisher ratio, and it's mean square between over mean square within. In the between subject case, if we have an independent samples design, this would be the mean square between subjects over the mean square within subjects. If instead we have a repeated measures design, we still have this structure, but now we're talking about the mean square between conditions over the mean square within conditions. But in all cases, it's going to be a mean square or a variance between over a variance or mean square within. As that red area that we saw just a moment ago is relatively large, it will tend to swamp the smaller areas that we had seen. This will give us a really small F ratio. If we now try to contextualize that F ratio in all possible F ratios that we see here in this distribution of F ratios, remember that this ranges from 0 to 1, and we were generating ratios that were consistently smaller than 1. So we go from 0 to some value less than 1 for each of the ratios that we had seen earlier. We need to get past this critical value. Somewhere between that critical value and positive infinity is the upper end of this distribution on the x-axis. We need to be out here in order to reject the null hypothesis, and in order to indicate that we're having a significant relationship between our independent variable and our dependent variable. So hopefully this familiar F distribution helps you contextualize that pie chart. Okay, so let's go on to a different variation on this. Now we'll keep all the conventions the same as they had been in the previous slide, but what we'll do here is just change the proportions that you had relative to those that we had a moment ago. Factor A is still in blue. Factor B is now in lime green as before. Factor A by B, or our A by B interaction, is going to be shown in yellow. And we might ask you which effects, if any, have a significant F value. Strictly speaking, we're going to need to compute this, but what we can do is develop some intuitions in our course where we really value quantitative reasoning, and we want to see just intuitively which of these effects would likely be significant and which ones non-significant. Hopefully it's obvious to you that using the logic that we just described in the prior slide, and also thinking about the distribution of F statistics, we can see a very large blue area in the numerator hovering over a relatively small denominator shown here in red. And that's going to give us a large F ratio. Almost certainly that's going to be a null hypothesis that we can reject. Stated another way, we probably have a significant effect for factor A. Similarly, for factor B, in this lime green area, the green is quite a bit larger than the red, so we're going to have a fairly large number in our numerator over a much smaller number in our denominator, and that's probably going to give us a statistically significant F value. Again, we'd actually have to have the numbers and know the degrees of freedom to make a formal diagnosis, but using our quantitative reasoning, just using our intuition, we can see that factor A will almost certainly be significant. Factor B, although smaller, probably is going to be significant. By contrast, if we look in this particular case at the A by B interaction, signified here in yellow, that area within the pie is about the same size as the red area, which corresponds to our within subject variability. Stated another way, we're going to have very similar numbers in our numerator and our denominator. That's going to give us an F ratio pretty close to 1, and we know that we need F ratios substantially greater than 1 in order to reject the null hypothesis for any given effect. So to sum up, in this particular case, we almost certainly have a significant effect for factor A, probably so for factor B as well, and we almost certainly won't have a significant effect for the A by B interaction. Okay, we'll go on to another example, and here you can see everything is equally sized, and again, here's our red area for the denominator of the F ratio. Because these are all equally sized, they're all going to generate F ratios equaling 1, and 1 would never be large enough for us to reject the null hypothesis. So none of these effects, factor A, factor B, or the A by B interaction, are going to be statistically significant. Here's one other one that we have, a relatively small red area, and relatively large blue, green, and yellow areas corresponding to factor A, factor B, and the A by B interaction. Each of these will generate an F ratio noticeably greater than 1, and perhaps even large enough to reject the null hypothesis. So in this particular case, it's important to realize that we could wind up with a significant effect of factor A, a significant effect of factor B, and the A by B interaction also as statistically significant. What I hope you recognize from this is that each of these colors shown here can vary independently of the other colors. And stated another way, it could be the case that we wind up with a significant interaction without having any of the main effects being significant, or vice versa. Each of these components is completely independent from the others. Sometimes it's a source of some confusion for students. They erroneously think that if you have a significant interaction, that the main effects have to be significant as well, and that's not the case. These are all entirely independent of each other. Okay, here's one last one. As you might see, we have a relatively large red area. Hopefully that sets up a flag for you, and then you understand quite intuitively that you've got a big denominator, and as such, you're probably not going to have a lot left over for the numerator. Here we've taken the numerator area. As always, we've partitioned it into factor A, factor B, the A by B interaction, and here we're getting a fraction very similar to 1 for factor A. For factor B, we're getting an even smaller ratio, and probably a ratio near 1 again for the A by B interaction. None of these are going to be significant. Okay, hopefully that was helpful, and we can begin to summarize in the following way. For any two-way between subjects ANOVA, the total variability can be partitioned into basically two broad categories. One's going to be the numerator category, one will be the denominator category, between subjects and within subjects. Between is in the numerator, within is going to be in the denominator. And so we can take the numerator and break that down even further into a factor A, a factor B, and the A by B interaction. Recall too that had we been doing a within subject ANOVA, also called a repeated measures ANOVA, we might have been able to quantify the consistent individual differences in one or more of those effects, one or more of those factors, and we would have been able to then pull that information out of the denominator, and that would have given us a smaller denominator, thereby increasing the chance of getting a big F, allowing us to maybe reject the null hypothesis in that case. Okay, why don't we have you pause the video just for a moment and jot down to this point what has been clear and what has been less clear. Okay, welcome back. We'll go on to our next idea, and the next idea is something called Eta Squared, but the question being, can you describe what Eta Squared tells us? Okay? Hopefully, whether you've looked on Wiki or whether you've had some other source of information, you've been able to tell us that Eta Squared is an indicator of effect size. And we'll return to the idea of effect size throughout this presentation, but that's the first bit of information to know, that Eta Squared is an indicator of effect size, just like Cohen's D is an indicator of effect size. And so is Kramer's V, a different kind of indicator that we might be using if we had nominal variables, and this would be associated with something like a chi-square analysis. We could compute an Eta Squared value for each main effect and for the interaction in any one of our complex designs, again, factorial designs where we might have a factor A, a factor B, and an A by B interaction. So this style should now look familiar to you. We've got a slightly different question on the floor. Instead of asking, do we have a significant F value, and that's a statement about, or a question about hypothesis testing and null significance finding, null hypothesis testing, what we want to know here is what's the effect size. This is the magnitude of the relationship between the variables of interest. So here, we're looking at this relatively large blue area, a smaller green area, a very small yellow area, and an equally small red area for the within subjects component. And which factor would likely have the largest Eta Squared? We'll let you think about that for a moment. Hopefully you're coming to the conclusion that the answer to this question is really very straightforward. The strength of the Eta Squared is really going to be given by the relative size of each of the factors of interest, factor A, factor B, and the A by B interaction. Okay? So one of the good reporting practices that we're going to be talking about in just a little while, and this comes to us from the American Psychological Association, is that we always want to be able to report not only what was the case or the findings with respect to our F statistic, or whatever statistic we might be using, but also some indication of effect size. So let's remind ourselves that the effect size is the strength of the relationship between variables. For example, we might report the proportion of variance explained for each effect. That would be for each of the main effects as well as for the interaction effect. Okay? So this is the idea of effect size. We've seen it before when we had Cohen's D. We've also mentioned very briefly Kramer's V when we were doing the chi-square analysis. Right, there's an important note here. There's more than one way to measure effect size, and there's just a little bit of practice that's needed in order to get familiar with what the different kinds of effect size might be telling us. Here we're going to be talking a lot about Eta Squared, and this is going to be reporting the proportion of variance explained by each of the effects in our analysis. So let's now just learn the new letter. This is the eta, which is the 7th letter of the Greek alphabet, and we're going to be doing eta squared. It's a relatively simple formula, and it's going to be based on the sums of squares. It's an important component that we've had when we've been talking about the variability that we might experience inside of our experimental design or research design. And that sums of squares is another idea that we'll return to later on in this video when we're talking about basic ratios. For the moment, we're on eta squared. This is the 7th letter of the Greek alphabet, and we're going to compute eta squared by looking at the sums of squares associated with the effective interest. As an example, that might be factor A. And we're going to use that number again here in the denominator, but add to it the sums of squares that we have associated for the within subject component in our earlier pie charts that had been shown in red. Okay, so we have that effect size, or excuse me, that effective interest in our numerator, that same number again, plus the SS within. If we have a large value on the left side of this equation, what might that corresponding pie chart look like? We'll let you think that through. Okay. If you have a large eta squared, then you would imagine that the corresponding color in our pie chart is going to be proportionately large as well. Okay, so this is really going to be scaling proportionately to the size of that effect inside of our pie chart. Okay, so the r squared that you might remember from earlier this semester and the eta squared provide exactly the same information. Both of these are indicators of effect size. They show us the strength of the relationship between the variables, maybe between, say, factor A and our dependent variable, or factor B and our dependent variable, or the A by B interaction in our dependent variable. And this is now expressed along the lines of the proportion of variance that might be attributed to that particular factor. Okay? So the r squared is telling us the same thing that the eta squared is telling us. In class, we'll do a very interesting exercise where I'll show you some F-tables that will come out of some software packages that we might be using, and I'll have you use Excel to try to develop the actual value of eta squared for each of the effects that we might have inside of a complex design. So we'll use an example here just to set the stage for what we're going to be doing in class, and we'll pretend that we are organizational psychologists, and we're interested in how maybe a Fortune 500 company is operating, and something about its employees' hours worked. How many hours are folks working, and might that be associated perhaps with gender as one possibility, and also with the employee's educational level. So we'll construct a simple factorial design. In fact, the simplest possible factorial design, we'll go with a 2x2. We'll have 2 levels of gender, and we'll have 2 levels of education. We'll call this education variable our MAST-DOC variable, and that stands for master's degree or doctorate degree. We'll put all the folks who have either of those advanced degrees into one category, and folks who are not similarly educated into a different category. So we'll dichotomize our education variable into those 2 levels, and then we'll cross that with 2 levels of gender, and we'll see what kinds of analyses we might have, with our dependent variable being the number of hours worked. Inside of a software package, you can easily put out these kinds of analyses, and here's some output that we might have from SPSS, for example. And you can see that we're getting an F-table for the gender effect, also for our educational variable, that's called MAST-DOC for master's degree, doctorate degree. And then we're getting the interaction between those 2 variables, our gender variable and our MAST-DOC variable. And we get the sums of squares, degrees of freedom, mean square, which is also a variance, and then the F statistic, which is, as we've seen earlier, the ratio of 2 variances, the variance between over the variance within, sometimes called our error variance in our denominator. So what we'll do in class is we'll have you make this computation inside of Excel. We're going to have you compute the eta squared, a measure of effect size, for the gender variable, and then for MAST-DOC, and then for the interaction of those 2 variables. Just to set the stage for that, we can remind you that we can pull right from the F-table the sum of squares associated with the gender variable. We'll put that here. We'll also get the sum of squares associated with the error term. That's going to be the 27,920.02 that we have here. We'll sum those 2 up to get the denominator of our eta squared computation. And then our numerator, again, will simply be the sum of squares associated with the effective interest. In this case, that's going to be gender. So you'd have 343.066 over the sum of these 2 values, and that will give you the eta squared for the gender effect. We can then repeat the exercise. As I've changed the slide here, we can now do the same computation, but we can look at what is essentially factor B. That's going to be our educational variable. our educational variable was operationalized as master's versus doctorate. We can pull off the sum of squares for that particular variable. We'll put that in our numerator. We need to develop the denominator, which is adding that numerator's value again to the sum of squares for the error term. We'll get a grand total there. And then we'll take the ratio of the sum of squares for mass doc over that grand total, and we'll wind up with the eta squared, or the proportion of variance accounted for by this factor b, which is our educational variable. Finally, we can do this one more time, and we can look at the eta squared for the gender by mass doc interaction. Okay, so now we're going to take that sum of squares. That becomes our numerator. It also factors into our denominator, along with the error term that we've been using all along, and we can compute the eta squared for that as well. So now we have a measure of effect size for each of our 3 effects inside of this 2x2 design. And we can now expand this just a little bit and see that many software packages, including SPSS, can provide that information to us directly. So if you're going to be doing these computations correctly, we should come up with effect sizes as indexed by eta squared of 0.012, 0.010, and 0.031. Remember that this is providing the same information as an R squared would provide. Okay, so we can get this directly out of SPSS. Okay, so we can have SPSS tell us about eta squared, or the effect size, for each one of our 3 effects in a 2-way analysis of variance. The main effect of factor A, the main effect of factor B, and the A by B interaction. We can also get a similar kind of information about a different construct, and this is the construct of power. And we've addressed this once before, but it's been a little bit of time. So let's see if we can now remind ourselves a little bit about power. And we'll start out with a potential pop quiz question. In your own words, explain what power is in a statistical sense. We'll let you pause the video and answer that question. Okay, welcome back. As you might recall, power is the ability to find an effect if the effect is there. Okay, so sometimes we'll be looking for an effect of factor A, or an effect of factor B, or the A by B interaction, and we might want to know what's the likelihood, or the probability, I should say, of finding that effect if in fact it's there. Every once in a while we might miss an effect that's actually there, but we want to know how likely it is that we would find it if it were there, and we can actually quantify that, and we do so using this construct called power. Okay? Let's see if we can develop that idea just a little bit further by way of this next pop quiz question. In your own words, explain why it is important to report an estimate of power when an effect is non-significant. And hopefully your answer will have some critical thinking supporting it, more so than something like APA tells us we have to report power. We'll let you stop the video and see if you can respond to this question. Okay, welcome back. Let's see if we can develop that idea a little bit. So why is power important, especially when we have a non-significant finding? Non-significant findings are very difficult to interpret. There are at least 2 very clear interpretations when we have a non-significant finding, and it's not always obvious which of these 2 is more likely. Let's see if we can develop that just a little bit more fully by asking you to think about something that's very, very intuitive, something like going on a fishing trip. Imagine that you're out on some lake, and you're interested in fishing, and you've got your fishing net with you. You stick your fishing net into the water, you drag it through, you pull it up, and you come up null. You have a null finding, essentially, parallel to the null finding that we might have in a research study. Now, why did you come up null when you had stuck your net into the water and came up with absolutely nothing? Why was that the case? There are at least 2 possibilities. One possibility is that this particular lake contains no fish. That is to say, by analogy over here, maybe there is no effect for the independent variable that you're investigating. A different possibility is that maybe there really are fish in that lake, and you just happen to have missed them. Okay, so there is an effect to be found, but you've missed it. And when we come up null, it's not entirely clear which of those 2 is really true. Is it the case that there is no effect whatsoever, no fish? Or is it the case that there really is an effect and we just missed it, so we missed the fish? What's cool about power is that power gives us some indication of the probability that we would have found the effect if the effect had been there. The higher the power level is, the more likely it is that we will catch a fish, in fact, if the fish had been there, or find the effect if the effect was in fact there in the environment. Okay? So we'll return to that analogy throughout the semester, but I think that sets the stage for understanding the concept of power. Okay, one other bit about power is it ranges on a scale from 0 to 1. Some people would quibble with that and say actually it ranges on a scale that goes from 0.05 to 1, because there's always this possibility that we're going to wind up rejecting the null hypothesis just by chance, just by having a type 1 error. And typically the conventional level for type 1 probabilities, type 1 errors, would be 0.05. Okay, so let's see if we can now return to some output that we might get in a computer-generated statistical analysis. And here we are again at the F table. We're back in our 2x2 design, and here we have gender, mass stock, and their interaction, as we had seen a moment ago, with their sums of squares, degrees of freedom, their mean square or variance, their F values. Here we have the Eta Square that we saw a moment ago. We'll go all the way over to the right-hand side, and we get some indications of power here. We're getting an indication that the power is 0.259 for factor A. That's the gender variable. An indication that the power for factor B is 0.224. That's going to be our educational variable. And then the gender by education interaction is generating a power level of 0.567. Okay, so again, this is the probability of finding an effect if it's there. In this particular case, it turned out that each of our Eta squared values would be shown here, but only one of these effects actually reached statistical significance. If we look at the sig value for each of these three factors, we can see that we have a non-significant effect for gender. We have a non-significant effect for education. Their interaction, though, did achieve statistical significance. It's particularly interesting to try to understand this observed power in the context of this null finding. We have null findings for factor A and factor B. So we came up with no fish, essentially. Did we come up with no fish because there were really no fish there, or did we just happen to miss it? Well, it looks like we didn't have a really strong chance of finding that fish, even if it had been there. We get values of 0.259 on a scale that goes from 0 to 1, and value of 0.224. These are not particularly high numbers on that range that we're interested in for power, from between 0 and 1, or arguably between 0.05 and 1. The American Psychological Association typically recommends that we have something like 80% power. That would be a desirable level of power, and then if you come up null, you've got some confidence that maybe there aren't a lot of fish in that lake, maybe there aren't any fish in that lake. But if you have very, very low levels of power, the probability of finding an effect, finding a fish, was pretty small to begin with. Okay, so that's our introduction to power and how it might help us with the interpretation of a null finding. We'll let you stop the video now and make a note of what has been clear and what remains unclear. Okay, welcome back. Now we'll talk a little bit about some reporting style issues as given to us by the APA, especially for factorial designs. It's important to establish good reporting practices when we're communicating with our audience, and we want to make sure that your audience fully understands what was going on in your research design. So when you're writing up the text for your studies, it's important that you indicate some indication, or you offer some indication of central tendency and also some indication of dispersion. Frequently, when you're writing the prose for your results section, you'll offer something about the means for your various conditions and some indication maybe of the standard deviation, occasionally the standard error, but some descriptive statistic along with whatever inferential statistics you might be providing. That's a good reporting practice. Okay, you will likely be required to do that in your psychology research courses, and I think you'll see that this kind of information is typically reported in any kind of legitimate journal that you might be reading, even in your everyday life. Okay, other kinds of reporting practices that we might want to mention, and I'll go through these fairly quickly because you probably can see these on your PowerPoint lecture notes, but just for clarity, we want to describe the variables and offer definitions of the levels of each of the variables that we might have. A moment ago, we had a 2x2. We described what the levels of each of those variables were. Summary statistics for cells of the design matrix in text, table, or figure, including, when appropriate, confidence intervals or group means. Okay, so again, some other way of summarizing the data for your audience. Report the F-tests for main effects, as well as the interactions. And ideally, you'd offer now exact probabilities. In decades gone by, we sometimes would simply report that the probability was less than 0.05 or not, but now it's fairly easy in the modern times to be able to get an exact p-value, and we prefer to give that to our reader just for a little bit more precision. The effect size for each effect, we might use something like Cohen's d or Kramer's v. Today we learned about Eta Squared, but some indication of the strength of the relationship separate and apart from the F statistic that we might be reporting. Okay. Some statement about power for the non-significant effects, so that we know whether it's more likely the case that there really are no fish out there, or that maybe there are some fish and we just happen to miss it because we had a relatively poor fishing net, we had relatively low power. Okay, simple main effects analysis when interaction is statistically significant. We talked about in our prior video how we have a hierarchy, a decision tree, through which we make our way when we're trying to analyze the many different effects that we have. And if we do have a significant interaction, we typically go to the simple effects. A verbal description of statistically significant interactions, if they happen to be present, referring the reader to the differences between the cell means across the levels of the independent variables. This harkens back to our subtraction method. Remember that we found different kinds of differences whenever we had evidence for an interaction. So instead of having the same differences, we would have different differences, and the APA is encouraging us to try to spell out those different differences to our reader. A verbal description of statistically significant main effects, when those are present, referring the reader to differences among the cell means within the level of each of those main effects. Analytical comparisons, these would be the post hoc tests that we might run to adjust for cumulative type 1 error, and also to help us pinpoint where the actual differences might be. And maybe we'll end with some conclusions that we hope the reader will take away from all of this analysis. So these are good reporting practices that we'd have really in any kind of research design. They become particularly important when the design gets a little bit more complicated, when we're looking at factorial analyses, for example. Okay, we'll let you stop the video just for a moment and make a note of what's been clear to this point and what needs further clarification. Okay, welcome back. We'll spend just a moment talking about some issues in SPSS, and we'll spend a little bit more time talking about how we might develop the basic ratios that are going to be needed to give us some of those pie charts that we looked at early on in today's presentation, the pie charts that contain the variability that we're going to partition into the between subjects components and the within subject components. For right now, we'll take a little peek at what we might see inside of SPSS, for example. We'll have some sequences for us to click on in class. Most importantly, SPSS and other packages will allow us to evaluate the assumptions on which our Factorial ANOVA rests. We call that an ANOVA is a type of test that we consider to be a parametric test. And all parametric tests are based on means, and they all come with a fairly complicated set of assumptions. Whenever we have an independent design, or independent groups design, we always have this equality of variance issue that we must address. And we've seen before that we can use the Levene test to tell us about whether our different conditions satisfy the equal variance assumption. Remember our rule, we look at the Levene test specifically, we go to the sig value, this is the observed alpha level, and this is, if this is less than 0.05, we need to reject the equal variance assumption. If it's greater than 0.05, we can retain the equal variance assumption and proceed on to step 2 of our two-step process, which is evaluating now the null hypotheses. Of course, here in a factorial design, we're going to have a null hypothesis, which calls for the equality of means across factor A, the same thing for factor B, and then for the A by B interaction, the null hypothesis would be that we don't have a significant interaction. Okay? So having satisfied the Levene test, we can now take a look over here in the F table, and in this hypothetical output, we happen to have a statistically significant sig value for factor A, and for factor B, and for the A by B interaction. Okay, so we can evaluate the main effects and the interaction after we've assured ourselves that in an independent subject's design, we have satisfied the Levene test for equal variance. Okay, so that's what the output might look like there. Now what we'll do is ask the question about how we might begin to compute this manually. Inside of Excel, we can put in our data and begin to look at such things as basic ratios that will give us the sums of squares that we're going to need to allow us to get to the F ratio so that we can evaluate the null hypothesis eventually. Let's take a practical example, one that I think you'll find very interesting. We'll go with a 3x2 design. And here we'll be interested in the problem of how it is that folks can solve puzzles or solve problems that are either complex or simple, as a function of whether the feedback that they receive might be relatively favorable, we'll call that condition praise, or relatively less favorable, we'll call that condition criticism, or another set of folks will receive absolutely no feedback whatsoever. So in this 3x2 design, we have 3 levels of feedback. Those are shown here in columns. We'll call that factor A. We also have 2 levels of the problem's complexity. We have relatively simple problems and complex problems. Okay, so in this design, we can say that in our different levels of factor A, we can assign a number to each of those levels. Factor A1, factor A2, and factor A3. We might even call those levels A1, A2, and A3. Same thing over here for our complexity variable. We can have level B1 or level B2. And what's nice about this is there are going to be times when it will be helpful to refer to a cell by this kind of abstract coding principle. Maybe cell A1, B1, and so forth. And we want to ask questions like this. How would we label, or what coordinates would we use to label the praise complex, as you see here? Okay. Hopefully, you've come to the conclusion immediately that because it's in the first column, it gets an A1, and because it's in the second row, it gets a B2. So we can refer to this as the praise complex condition, or we can call it condition A1, B2 to stay in the more abstract. And this would allow us the possibility of describing any kind of 3x2, not just one that's based on something as specific as, say, feedback by complexity. Okay. Inside of Excel, if we're going to make these manual computations, typically we put each of our different conditions. Here we have a 3x2. That gives us 6 different conditions. We put them each into their own column. And we might give them labels that are practical for the particular case here, praise simple, or equivalently, we can give them the more abstract name of A1B1, A2B1, and so on down the list. Okay? What we're going to need to do for computing the basic ratios that'll get us to the sums of squares, we'll need to take the sums in each of these 6 conditions, and of course we have 6 conditions because it's a 3x2. Okay? So just to give you an example, we can add 7 and 8 and we get to 15, 6 more would get us to 21, here's 10 more that gets us to 31, here's 7 more that gets us to 38. We can begin to summarize all of those sums in an AB matrix that we see here. This is called the AB matrix of sums, and you can see here that for condition A1, B1, we have the sum of 38, which we just computed. We can do the same thing for each of the remaining 5, and we get these sums, and then we can take some column sums to get to something akin to the main effect of factor A. Correspondingly, we can take the row sums to get to something like the main effect for factor B. Okay? So we get the AB matrix of sums, as we've done before, and then what we'll do is square that, as we've done in previous sections. And once we've got the squared version, we can begin to make our way toward the basic ratios. Okay, so the basic ratios are going to be something that we'll do in class. And remember that the basic ratios are going to help us get the sums of squares. And to appreciate that, we're going to learn about some new basic ratios today. And these will be the last basic ratios that we introduce in this semester. We're going to manually compute a factorial ANOVA, and we're going to do so using some of the basic ratios that we had done in that we had used in prior sessions. But we're also going to introduce some new basic ratios. We'll have one for factor A. We'll call that basic ratio A. One for factor B. We'll call that basic ratio B. And the A by B interaction will be signified by the basic ratio AB. So here will be a handout that you'll get in class, and you'll see some old friends. You'll see some y and t basic ratios, and these will be computed as they always have. Nothing new there. What is new is that we now have an AB basic ratio that will correspond to the interaction term. We'll also have one for factor A and for factor B. We'll go through these details in the classroom. Once we've got these computed, all we then need to do is mix and match them within the sums of squares column of our F ratio table. And as you can see here, we'll do something like A minus t to get the sums of squares for factor A. We'll do B minus t to get the sums of squares for factor B, and we'll do this longer computation. AB minus A minus B, careful, plus t, remember that, plus t for the A by B interaction. And then finally, we'll have an error term. And with these sums of squares now computed, we can divide those by the degrees of freedom. And as we recall from even the earliest weeks of class, sums of squares divided by degrees of freedom will give us a variance. Our fancy phrase for variance is mean square. We'll get a mean square for factor A, factor B, the A by B interaction, and also for the error term. and we'll put each of these in succession over the error term to develop an f-statistic for all of them, just like we had done on the opening slide of today's presentation. We started out with this big circle filled with variability, and we colored the different components that had been partitioned into the within subjects part, which was our denominator, and the variously colored components of our numerator, the between subjects variability, factor A, factor B, and factor A by B. Okay, so that brings us to the end of today's conversation. We've introduced lots of new ideas. It's important that you jot down what has been clear here. This affirms and concretizes your metacognition. Also, please jot down what needs further clarification, and we'll look forward to taking your questions in class. See you in class.